In this lecture, we shall discuss some problems on elasticity selected from various competitive examination papers. And some problems might require knowledge not only of this chapter, but some other chapters as well. So let us go for the problems one by one. So here is the first problem coming, and this one is telling that a thin rod of negligible mass and cross-sectional area 4 mm square suspended vertically from one end has length 0.5 meter at 100 degrees Celsius. The rod is cooled to 0 degrees Celsius but prevented from contracting by attaching a mass at the lower end. Find in part A the mass, part B the energy stored in the rod. Young's modulus of rod's material is 10 to the power 11 Newton per meter square, and its coefficient of linear expansion is 10 to the power minus 5 per degree Celsius. So see here, there is a new term for you, coefficient of linear expansion, and this part requires we have some knowledge about thermal expansion of a solid, and I shall introduce that at right time in the problem. We shall understand the problem by drawing a figure here. This is a ceiling shown, and from here a thin rod of negligible mass is suspended. The original situation where the length of the rod was given to be L. I'll write down the data also in a short time. But first of all, let's understand, as the rod is cooled from 100 degrees Celsius to 0 degrees Celsius, according to the principle of thermal expansion and contraction, the length of the rod should decrease, and the situation should be something like this, where I am showing a tiny decrease in the length of the rod. So I can show it as well, the dimensions, by drawing these horizontal lines. So the tip of the rod at these two conditions, and here you see the original length of the rod was L, right? So this L is given to be 0.5 meter, and the cross-sectional area of the rod, this is a circular cross-section we assume, and this cross-sectional area is also known to be 4 millimeter square. Converting to SI, this is coming out to be 4 into 10 to the power minus 6 meter square. And you see that as the temperature has gone down, under no other effect the length should have gone down from this to this, and therefore this distance is standing for delta L modulus, where delta L is standing for the change in length. Since the length has decreased, delta L should be a negative quantity, so I show here the dimension to be delta L, that is the absolute value of change in length. So this was situation if there was no other effect, but they are telling by attaching a mass at the lower end of the rod, this possible contraction in length of the rod is stopped. Therefore, I introduce one more figure, that is at the same time as the rod is being cooled, if a mass is suspended, suppose the mass of this block is M unknown, at the lower end of the rod, then the possible contraction is balanced, countered, and therefore the rod retains its original length. We might conclude here that a contraction in length takes place because of cooling of the rod, and then followed by an expansion in length happens, and that expansion in length must again be equal to delta L modulus only because of the tensile force exerted on the rod by hanging this mass. So this is the way you should understand the problem. Although the two things, contraction and expansion, taking place simultaneously, but my figure is showing that the two effects step by step. First a contraction of modulus of delta L, and followed by an expansion of delta L modulus because of this tensile force created by the force of gravity on this block. So let us see what they are telling further. They are telling initial temperature of the rod theta 1 was 100 degrees Celsius and the final temperature theta 2 is equal to 0 degrees Celsius. The Young's modulus for rod's material, that is given to be 10 to the power 11 Newton per meter square, and the coefficient of linear expansion of the rod's material alpha, the symbol for that is alpha usually, is given to be 10 to the power minus 5 per degree Celsius. Let me introduce a formula here for you from thermal expansion chapter. It says that the change in length of a rod because of change in temperature is given by the original length L0 into expansion coefficient alpha into change in temperature delta theta. In my case, L0, the original length, let me write it to be L0 to avoid any confusion. This L0 is 0.5 meter, the original length of the rod. This is this one. Let me call it L0 here as well. I'm talking about the actual original length of the rod in my first figure. So, the value of alpha is given to be 10 to the power minus 5 per degree Celsius, and delta theta, that is final temperature minus initial temperature. Never miss the order. That is theta 2. Let me write it here as well. L0 into alpha into theta 2 minus theta 1. Theta 2 is 0 degrees Celsius. Theta 1 is 100 degrees Celsius. Therefore, delta L is coming out to be a negative value given by minus 5 into 10 to the power minus 4 meter. So, as expected, I have seen here that the length of the rod has decreased. Therefore, the corresponding expansion caused by the tensile force produced by the force of gravity on the block, this must be equal to delta L modulus. Contraction and expansion must be equal in magnitude, that is plus 5 into 10 to the power minus 4 meter. Understand this.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.